Okay, so the chapter 2, we are going to talk about fundamental equation for more complex flow. Because in your undergraduate, maybe you are talking about the incompressible non-rigid. Okay, so in that case, we become to the ideal flow, become to a binary equation. But in reality, flow may be compressible flow with viscosity. So this will become to the real fluid. Okay, so we be different from your undergraduate fluid we are talking about. So, but mass conservation equation without too much difference. Just a little bit more different change because it become to a compressible. So density may be changed. It's not incompressible. Density is a constant. So for this part, mass conservation equation, we still use material or particle derivation. This is from the Lagrange coordinate. For Lagrange coordinate, we look certain of a parcel. This mass doesn't change. Maybe then we compress. That means density will change and the volume will change as well. So, but the mass we conserve, and the mass is due to the density and the volume. So if we take this as the Lagrange, that's still constant. So if we take a Lagrange or the material derivation, this should be like the 0. So because they have a two component, density and the volume. So if we take the density out, we only consider the volume if they change with a different time. Similar, volume with a constant, then density if they change with time. So this is the total differential. This should be described by the Lagrange because we use a material derivation. Textbook has some typo. Textbook, they say this is a Euler coordinate. I think this is a kind of confused. So as long as you use this, it's you follow the certain of particle. Okay. Later on we will show what kind of a form should be the Lagrange, but should be the Euler because the Euler is for the control volume. It's all by the space. You just look at the fixed location, x, y, z. That should be the Euler coordinate. Okay. So for this Lagrange coordinate, we look this equation, and if we divide by the volume, this equation can rewrite like this. Volume we divide, and this part, density for this total differential is a constant. So we just need to look if this volume change with a different location. And this part we define as the rate of a volume change because the volume, original volume, and later on, if this volume change. So if we use the definition of a volume for the calculus, this volume can define by the different sign x, y, z. And the new volume can be defined by their change rate. So this delta x may be increase or decrease. So you have a delta x, delta y, and the delta z minus original volume. Okay? So for this, you can see we need to use a first order approximation. So that means we only consider the delta x times the delta y and the delta z. Okay? We don't consider delta x, delta y. If they tie together, that will be the second order. And because this delta x, delta y, and the delta z is very small, so you consider if this is like one, maybe this is 1,000, okay? This is one. Then basically, we don't consider this time is one, okay? So use the first order approximation, second order, and the third order. For example, third order, delta x, delta y, delta z. This is even smaller. We don't consider the small order, okay? So for this, we will get this kind of variant change rate is related to the very epsilon. This is like extension and the compression. Just like we mentioned, this is by the partial x, partial u, depending on the velocity difference in the space. Okay? Okay, so the mass conservation equation, this one, if we rewrite into the density material derivation, that means we follow the individual particle or individual parcel of fluid. And also we follow the individual of parcel of a bottle. For this bottle change, we can write down as dilation or the extension. This is just like we mentioned before. This is related to this one. Okay, this is we introduced in the kinematic in the chapter 1. Okay, and for this we become to a diverge velocity. So this part we become to a diverge of a velocity. And you can see this one usually in your special case in compressible flow. In compressible flow, this term it become to a 0. Okay? But in the compressible flow, it's not. In compressible flow, you should summation this part. So you can see in the incompressible flow, this term, because the volume doesn't change, this becomes to a 0. If we follow the density, it also doesn't change the density for the incompressible flow. Of course, this also becomes to a 0. Both terms become to a 0. But if the compressible flow, for example, density increase, that means the volume reduce, right? If density increase, that means volume reduce. So that means if this increase, this must be reduced. This become positive, this become to negative. Summation become to a 0. Okay, so that's for the compressible flow. So for the compressible flow, basically, this term is the Euler description because we already use the space and the velocity to describe that. This is a constant. For this, we need to use the material derivation to get the local term and the convection term. Okay? Also, if you use summation this term and this term, you can rewrite as this one. Okay, so for this one, it's a local derivation. And for this, if you expansion, then we become to this 2. Then before we talk about index notation, it's useful, right? Index notation can show you how to use this one to become to this 2. But the first step, similar like we mentioned before, this term should be a vector because we have a scalar kind of vector. This should be a vector. Diverge vector, then we become to a scalar. So this term should be a scalar. Similar, this diverge vector, this will become to a scalar. Okay, scalar times scalar. So this also vector dot gradient. Now we cancel out the direction. This will become to the scalar. But then we have 3 derivation. Okay? They have 3 derivation. So for this is a good practice for your index notation. Okay? So I think this one or this one, we can mention this as a Euler term because they are differential in the space. It's described by the space parameter. But for this should be the Lagrange because we need to follow the individual particle. So if you follow the individual particle, your space parameter are changed because later on they maybe go to a different kind of a location. That means x, y, z change, but we consider fixed particle. Okay, so this should be described by the Lagrange term. Okay. Okay. Another mass conservation equation is important for define the stream function. In the most of the undergraduate consider the incompressible flow, then density is not considered because the density is a constant. But if we consider the compressible flow, the mass conservation equation will become to this form. For the steady compressible flow, because for the steady flow, this term will become to a 0. So we only have this term. But usually remember should be the 2D. Because the 3D, we cannot solve the 3D problem. For the stream function, is usually we reduce the 2 unknown to become to the 1 unknown. So 2 unknown for this case is a low U and the low V is a 2 unknown. Then we use the phi to represent this 2 unknown. So in compressible flow, usually it's the U and the V is a 2 unknown. Then use the phi to represent this 2 velocity unknown. Three different kind of unknown. For example, UVW is very difficult to reduce to the 1 unknown. Okay, so here this 2 unknown should satisfy this relationship. Then we use a new unknown phi to represent this 2. So let's still come back to the mass conservation equation. Because in this, you substitute in this equation, then previously in this equation, we have a 2 unknown, like this 2. Then we will reduce this 2 equation to become to the 1 equation, phi. And this phi must satisfy this relationship. Because if we put this relationship into this equation, then we satisfy. Okay? Original 2 unknown. Substitute this equation into here. Then we only have a phi. Because the phi, they will automatically cancel out to each other. So still satisfy mass conservation equation. So basically, use a stream function is to rewrite the form of a mass conservation equation. For example, for the compressible flow, we have this 2. Then we will write down become to this. Then because the total differential for this one, they automatically satisfy. So for incompressible flow, we have U and the V. Similar, we use the new unknown phi to satisfy U and V, these 2 unknown. Then another stream function is their definition is on the stream line, they are constant. So you make the differential, they will become to a 0. But if the 2 stream line with same gap, for example, stream function like 1 and 2 and 3, in the between, this is related to the flow rate. Because for this, that will become to a velocity times the normal direction. So that will become to the flow rate, and that will become to the flow rate between these 2 stream lines. And along the stream line, the flow rate will be 0 because there is no flow rate close to the stream line. Okay, So this is the mass conservation equation related to the stream function. Okay? Okay, so our midterm we go here to here to the mass conservation equation. Okay? So any question? Okay. So I will give you some do by yourself homework about this structure, so you can make some practice to get an idea about the mass conservation equation as well, and relate to the stream function. Okay.
So the middle exam just only include the chapter 1.
Chapter 1 and the mass conservation equation.
And today's subject.
Mm-hmm.
Okay. Thank you.
So no more methods. But maybe viscosity, right? Viscosity, we talk about viscosity, they have a velocity, have a shear strength. And the exam is open book, open note. Okay? But you should make sure your book and the note on your table not go to other students' table. Okay?